Boom. Screen share. Wait, mic's there. Let's start. I'm gonna go get water.
Okay, so I will get started with session number 7. In this session, we're going to primarily talk about autoencoders, and we'll also talk about how do we scale deep learning models, primarily using Apache Spark. So in the last session, we looked at using different parameter tuning options, figuring out how you actually get better algorithms by tweaking many of the parameters, which you can use Keras to do so. Here we're going to take an alternate approach. Rather than just changing the parameters to get a better performance for the deep learning algorithm, how can you do scaling? If you wanted to test out different iterations of your algorithms and see if you can use Spark to do that. Okay? And we'll kind of talk a little bit about the rationale and why you would want to do that, and then go from there. So, but let's first start out with autoencoders. How many of you have looked at autoencoders at all? Okay, so we have 33% audience who know what autoencoders are. Okay, so we'll primarily talk about autoencoders, which is basically a way in which you can take the data and get a latent or hidden representation of that particular set of features so that you can uncover the original representation. Okay, and it's basically an autoencoder decoder mechanism. And we'll also talk about scaling, and we'll also talk about some of the applications which are predominantly used for autoencoders. Now, one of the things which people talk about when they talk about deep neural networks is this challenge of, well, I have so much data to start out with. Is there a way I can basically do some pre-training of the model so that my deep learning models can converge faster, right? And some of the initial efforts were to figure out whether we can come up with a hidden representation or a reduced representation of my original feature sets so that I can start using my hidden or my reduced dimensions as inputs to my data. So, kind of going back to what we were doing before, feature engineering, potentially, wherein you are extracting certain features of the data and basically using that as your inputs for your deep neural networks. Think of it as like a PCA, or a principal component analysis, which is basically looking at a smaller set of dimensions which captures the variance in the original data set, right? So let's kind of get a little bit of intuition. So this is primarily an unsupervised learning technique. You typically do not have any kinds of labels built into the data. So this is your classic clustering problem, right? So you have your data X and Y, and you could basically use an algorithm like k-means or any other clustering algorithm to basically cluster into multiple clusters. And then the goal would be, if I have a new point, I want to find out what's the estimate, probability estimate for that particular new point, right? Now, if I have data which is complex, right? Typically when we think of looking at images, now if I wanted to do clustering, whether these are playgrounds or these are rivers or they're bridges and thing, we had a student team from Northeastern taught a course last semester who were looking at classifying different kinds of roof types, and also looking at densities of areas where you had similar kinds of homes, or if areas where there is dense population of homes versus other kinds of areas. So they wanted to do some clustering before and then start classifying whether there are different kinds of roof types that are built into the data. So the question is, how do you actually go about doing those kinds of things? So one technique, if you look at some of the literature in the late 2000s, you do see a lot of reference to autoencoders as a training mechanism before you can start deep neural networks, because the challenge was still there on how do you actually start with really large-scale data sets to start training deep neural networks. So the network is pretty simple. In this particular case, let's take the simple example we've been looking at. You have a picture of a cat, and it has a particular dimension, 3172 by 2123. And the goal is, can I build out a network which can compress it into, or bring down the representation to a smaller set of dimensions, but in such a way that I'm going to be able to retrieve back the original image, right? And in that particular case, if I just go back to what we had before, your traditional weights and biases. So each neuron will have a set of weights, and you'll have a bias. And then if I basically kind of denote them as W1, W2, W3, W2, and kind of just denote all the weights, and I basically have this data because the input and the output data is basically the same. And the goal would be to train my weights so that I can uncover that particular network, which will give me the hidden representation. Yes, yeah.
We can just note that the arrows on the right should all be pointing to the right.
Yes, we still have the typo in that slide because it's a mirror representation. The arrows should be pointing onto the right. Yeah, it's not going to fix that. So we'll have to fix that next time, the iteration around. Okay, so the question would be, how do we actually learn the representations, right? So here, we can learn some kind of a compact representation. As you can see, if I start with this is just a single layer autoencoder decoder network. So the goal is basically coming up with that middle layer, the weights for the middle layer, so that at that point I could say, well, that would be my compact representation of my inputs. Because using those as my input, I can uncover the respective attributes for my output, right? And if I basically start expanding the number of layers, and I could have like multiple input layers, and I can train each one of them separately, then I'll have like a deep autoencoder network, right? So here, that's basically what we're saying in here. So because y and y hat are basically the true representation and the recovered representation, and v would be the hidden representation. Then this layer v can further be split into, well, if v is my input, then I need to uncover this hidden representation w, which can recover the v hat. So similarly, I can expand those first. So I can do like layer by layer, see if I can uncover hidden representations there. So ultimately, I'll be able to come up with a deep autoencoder network wherein the z will be able to uncover the rest of the layers. Okay. So if you, let's say, take this is just an example on dimensionality reduction. So this basically is an example. This is like the third layer for an autoencoder trained on a data set of faces. So as you can see, that this layer has kind of captured some of the major attributes of a face: the eyes, the position of the nose, the edges of the lips, and things like that. So if you're trying to do like recognition and trying to uncover those images, it has been able to uncover many of these hidden representations. Okay. So let's kind of see an application on what you could do with an autoencoder. So here, what you're seeing is you have you're basically training a network, and you want to be using it as a classifier. And you basically take this original representation of the data, come up with a hidden representation, and use this hidden representation for your classification. Whether I'm classified as a cat or a dog or whatever it is, right? So you can then, at that point, this last layer which was used after you are done with your training, the last layer which was used to decode and get back the original data, you can knock that layer off and then just add some kind of activation function so that you can basically use that as a classification at that point. Okay. So other applications, one could be denoising, wherein let's say you have an image with some kind of a noise built into it. It's basically a noisy image. It could be pictures taken at night when there's a lot of noise in your images, and you want to basically remove the noise. So you could use a network which could basically extract only the key pieces of the image and kind of ignore the noise. And I'll show you some examples in the Keras blog. Okay. Another example could be to clean up images if there are specs in the image or really old images. You're kind of trying to uncover old data. You can kind of do that. Also to enhance the image resolution. So if you're trying to take small picture and cover larger picture representations, you can potentially do that too. So there are some interesting applications, and one of the primary applications which people talked about when they started talking about autoencoders were to use it for pre-training. And in the first few years, people said that's probably the best way to go about working with deep neural networks. Start with an autoencoder-decoder network. Use the hidden representation as the input for your deep learning networks. But that discussion has kind of died out in literature. A lot of people just say, traditional, whatever deep neural network architecture you choose, given sufficient number of layers and choosing a particular architecture, you don't have to go about starting out with a deep autoencoder network per se. Something to add?
I think people still recommend it if you have lots of unlabeled data and only a little bit of labeled data, right? Because you can then learn a good representation from the unlabeled data and, get more value out of your labeled data. Most of the time, just in many big applications, people now have enough labeled data. They just go directly to it.
But I'm not quite understand when you say you have unlabeled data, how do you leverage this one to apply to unlabeled data?
So if I have a billion photos,
A cat, right? So many cats, just like the cat.
well, I have lots of photos that some of them are cats, some of them aren't, but they're not labeled, and I have 1,000 labeled examples. You can use an autoencoder to try to learn the model, that can come up with a representation that's useful, that somehow captures a lot of information from your billion unlabeled photos, right? And then you can basically use those weights. So that's what the previous slide had, where you get rid of the decoder network and use that bottleneck in your network to say, I'm going to take this image and convert it to 1,000, say, numbers, right? A fixed size vector that we know captures a lot of the information about the image because we can reconstruct the image from it. And now I can use those, I can compute that for my labeled, or for any new photo, right? I can compute that vector. And now I can build a classifier just in that 1,000-dimensional space, which could be, an SVM or just a linear classifier or something. And then for any new image, I can feed it through my encoder, just the first part, get that 1,000-dimensional vector, feed it into my classifier, and get a classification.
But why not just use this whatever your data to train a classifier and put your unlabeled data into classifier? Would that be?
But how do you train it without labels, right? That's the point. If I don't have labels, then I can't train a classifier.
Even original data, you don't have labels.
Right. So if I have 1,000 labeled things and 1 billion unlabeled things, you can still learn a lot of useful information from the unlabeled data. That's like you basically build a model here's what these kind of images look like, and then once you have that model, you can use it to build a classifier just using your small amount of labeled examples.
So you are more like apply to the auto clustering problem, or you want to use the more traditional KNN algorithm like thing you say?
I mean, you can do whatever. You can just use anything. Yeah, you can use any traditional classifying algorithm. You're basically doing dimension reduction at that point. You're using an unsupervised learning technique to do dimension reduction, and then using any of the classifiers which has already been trained to take a 1,000 dimension vector or whatever that size of the dimension is to get you your labels. So that's another application. Now let's kind of take a look at an example. So this one's actually from the Keras blog itself. I'm sorry. Okay, I think I'm just gonna, yeah. And the escape button is end show. Okay, so let's get this link. I presume new tab. Okay, so on the Keras blog, there is a nice post on how do you actually build autoencoders in Keras. They've kind of given a bunch of different autoencoders you can build. Now, there isn't a model in Keras. Keras, you saw, you can build a sequential model, you can build a convolutional 2D model, different kinds of models in Keras. There isn't like a specific model called an autoencoder in Keras. Okay, but you can use other abstractions to actually build out an autoencoder. So the way you do it, so let's say going back to the MNIST problem. So I want to basically take this 28 by 28 pixel image. I'm going to pass it through an encoder and come up with this compressed representation and pass it through this decoder to get back my reconstructed representation, right?
So the compressed representation has to be smaller than the original.
Well, that's the whole goal, right? Because if you maintain that larger representation, then you are not basically, you already have information in this space.
Right. But I mean, like for instance, the CNN,
Mhm.
it wasn't. It's not necessarily like that there is any kind of layer. Like we actually build like more and more information. So
Well, usually,
there's no like
usually
collapse.
again, right?
At the end, maybe.
Usually for a classically trained network, you kind of get some, but it's not quite the same, but it's, I guess here the idea is you're keeping kind of all the information in some way, so you can reconstruct the original. In a classifier CNN, you have all the information that is relevant to actually solve your problem, right? So the early layers might actually completely get rid of stuff that's just irrelevant.
Now, ultimately,
But in the end, like those last layers are still fine.
But I mean, like if it's more information, then it's not going to work, correct?
well, you can potentially, you'll have a lot of redundant information if you have more information. If you have a layer in here, which actually, there are going to be a lot of redundant information. You could have represented it. I mean, if you basically have a layer which is exactly the same size of the layer as your input layer, then there's like a one-to-one mapping, right?
Exactly.
Exactly, right? So, but then if you have like a layer which has more pixels, then arbitrarily it will probably do that one-to-one assignment to different neurons, but then some of them will be left as redundant, will have like 0 weights, right? So in the context of what we're talking, we're trying to get to a hidden representation, which will basically remove that some amount of redundancy, right? So if we are trying to like build out a model, so let me show like a code example in here. So here we are basically taking this MNIST image. So here the encoded dimension. So we have like a 28 by 28, which is 784, right? So it's a vector of 784, which captures the information for each one of your digits. And we are trying to bring it down to a 32 vector of 32 by 1. Okay, so it's basically using a compression factor of 24.5 in this particular case. So the goal is, can I represent a 784 by 1 vector into a 32 by 1 vector, and can I uncover information which was represented in this 784 by 1 vector? So we're just doing, we are creating an input layer, specifying the shape. We are creating this encoded layer, specifying this dimension would be 32, and we are using an activation function again, ReLU. For that, we are passing this input layer as an input. For the decoded layer, we want this 784 to be recovered, and then we just use an activation function for sigmoid, and we use this encoded layer as an input, right? So this autoencoder, it's basically a model. You specify the input image and the decoded image, and the encoder basically is your model representation, and then you have the same or a similar representation for decoding. And then you compile your model, and just to kind of show how it looks, if you use matplotlib, so this is basically the input representation, the 784 by 1, and then you reconstruct this, and this would be like the recovered representation. But the goal is this recovered representation was recovered from my 32 by 1 vector, not the original 784 by 1 vector. So I could technically like take off the decoded vector, and if I wanted to train my MNIST, so I could basically use my output of the encoder layer and use my 32 as my input for any of my classifier. If I could do a traditional logistic regression or any other classification algorithm I could use for doing a multi-class classification problem, right? So and then they actually give some more examples. This is by it's a regularization example. So they import regularizers and then basically add some regularization constraints, and then kind of say that you can actually visualize it with I think the training loss, the test loss was 0.11. So you actually see by adding regularization that you actually got a little bit improvement of 0.01. Okay. And then an example for deep autoencoders, if I wanted to add multiple layers. So I start with 784, bring it down to 128, bring it down to 64, bring it down to 32, and then go back up, 64, 128, 784. So rather than going down from 784 to 32, so you're basically adding multiple layers and then kind of going back to get back 784. And in this particular case, it reaches 0.097, which is a little bit better compared to that of the prior models we had. Okay, because you have many more weights and many more parameters you could potentially get to. And then there is also an example for convolution autoencoder. It's kind of very similar representation. You start with a 28 by 28, then I have a feature patch through a 3 by 3, and then build out a convolution 2D layer, adding max pool layer, another convolution 2D layer, 8, 3 by 3, another max pooling layer, another convolution 2D layer. So the point is, you're taking this representation, and you have a representation which is 4 by 4 by 8, which is like this 128 dimensional vector. So you started out with 784. So you've kind of had this 4 by 4 by 8 representation by using convolution 2D.
And the other one was 32.
That was just a flat 32. Yeah. So this here you still maintain the convolution 2D architecture, and you kind of
Here, in this case, he's ready to have 4 times as much space in that pressure representation.
Yeah.
Here, it's 128 numbers. You could obviously do 128 with the other one as well.
right.
Yeah,
Yeah.
I mean, like, it's not a very fair comparison to the other.
Yeah, I mean, it's not a comparison. It's just basically different approaches you could use for building autoencoders.
It would be nice.
So then you go back from max pooling to upsampling, and you do an upsampling. So this is where you can think about changing resolution of your images. So if in that case you want to change your image resolution to a different size image, you can upsample and get an output. So you're basically going from this 8, and then you're kind of coming back to your original representation. So because right now you have this 4 by 4 by 8 dimension, right?
It's basically the inverse of max pooling.
Right.
Oh. Exactly. So I actually don't remember exactly what algorithm it uses, whether it just replicates pixel 4 times, or whether it's doing something more clever, interpolation. With the dots. I actually described it in the text here too.
Yeah. So the whole goal is like you're uncovering the original representation and getting back to the original representation. Okay. So if you use that, and they've given some examples on how to use TensorPort. So this is how the loss kind of gets down. This is the validation loss, and using this approach. So this is kind of the output, and the kind of basically looked at this hidden representation, this 128 representation. If you look at it, so this would be how the hidden representation would look. This is actually the representation for the various digits. I mean,
Interesting. He doesn't really talk about what you can or can't see in it. I don't really see much that's interesting, but
yeah. So I mean, it's just to kind of.
Different, is this all different digits? 1, 2, 3, 5.
So this is for the range 1 to 3, 0 to 9.
Okay, interesting.
Yeah. So you're kind of going through the whole range and looking at that particular shape, and then flattening it, kind of seeing the representation.
Okay, it's not 0. It's 0. It's for the 10 images.
Yeah.
So you can go try to see. Okay, here's what a 2 looks like. Here's what a 3 looks like.
Yeah, in this 128 dimension space. Okay. Another example for denoising. I think this is a nice example. So if you basically take the images and add Gaussian noise to it, and you kind of have this as your image, and you could use a network like this, and then you can actually uncover the original images and remove the Gaussian noise which has been embedded in this in these images. Okay. So then he also talked about there's a Kaggle data set which you can originally start out with. and see how your algorithm performs. And we talked a little bit about, we haven't talked about LSTMs, have we? Already? Oh, right. Generator had RNNs and LSTM. So sequence-to-sequence autoencoders. So this is how you represent. There isn't like a full example, but this is how we would actually do it. There's also variational autoencoders. So some additional examples. Okay. So that's a little bit about autoencoders. I mean, the whole goal. How do you actually start back the show? Yes, is that good? The point is, if you have use cases wherein you think that you could start out with a compressed representation rather than original representation, this may be a good tool to use. And in case you're trying to do denoising and then start out with the cleaned up images, that may be another good use case for autoencoders. Okay. Any questions? Yes.
It looks like it would work well for, I mean, if you can start, if you can compress, and I know it's a lossy, so you do something,
Right.
but I wonder if there's other applications like file compression or anything outside of just using as a way to get labels for your data, give on the data, or any other kind of applications.
So the labeling part, what Victor was discussing earlier is, if you have like a small data set with labels, and you have a large data set without labels, it's a good way to kind of train the network so that you can start with a hidden representation. When you talk about file compression, what are we talking about specifically?
So I think a little bit. So basically, file compression is something that you use for things along these lines. So one thing you can do is, if you find a good compressed representation of some particular image type, right? So I need to send surveillance camera images from a camera looking at a road. And maybe I can encode that. I can train on something that works better than JPEG or from generic image compression algorithm. I can send the compressed thing and then decode the other side. One place I know people do something like this is for resolution on tree.
Right.
So you take an image, you downsample it a bit, send it across the wire, and then use something that you use to approach like this to train an upsampler. That's better than just some kind of linear interpolation to upsample it again. So again, for mobile networking stuff, it's similar ideas.
Okay.
So these super resolution mechanisms, right, where you take your high resolution thing, you compress it down, and then try to train the network to say, okay, given the low resolution version, how do you run the high resolution version? If you can do that, now you can send people low resolution versions and then convert it back to high resolution. On the other side, it's not word basically because it figures out what I should do with different kinds of partial image.
Yeah.
There was I think also Google those Razor
For the images?
for image upsampling,
Yeah.
how they save bandwidth for mobile.
I don't know whether they talked about the deep neural networks or autoencoders, but it was kind of a similar concept wherein, in case they wanted to transmit a high resolution image to your device, rather than transmitting the whole high resolution image to your device, they'd actually send you a version of the image, and you basically have an algorithm on your mobile device to basically get back the original representation. So it's not technically you uncover the entire representation or the original image itself, but the algorithm does the compression. So the algorithm is used for the compression aspect of it. I think that particular algorithm was uncovering, or rather getting back the original image itself rather than compressed image of the image. Yeah. Okay. Okay, so the next segment we're going to go is talking a little bit about scaling in terms of how do you actually scale these kinds of models, right? Now, when we talk about deep neural networks, yesterday we kind of got an introduction to the complexities on why deep neural networks weren't really popular the first 10 or 15 years, since in the late 90s, and now why has it gotten popular? Now, things to look at now is what is actually driving the popularity of deep neural networks. One of the things is using GPUs, right? Because as you can think about the way you can compute your derivatives on GPUs much faster compared to that of CPUs, so that's actually making usage of deep neural networks much more popular. Now, another thing you could think about when you're trying to scale deep neural networks is, there's this whole notion of model compression. I think there was like a KDD paper in 2006, I guess, which primarily talked about what model compression is, kind of using memory optimally. So that's another thing you could use to efficiently reduce memory. But then you could also think about the computation of the gradients themselves. Can we, instead of you doing everything locally using GPUs, can we distribute the computation of the stochastic gradients? And one thought could be to use clusters or use distributed STD mechanisms, and we'll talk a couple of approaches to do that. And a couple of other things you could think of is you want to be able to measure what kind of things are, when you kind of compute these measures, how can you optimize? One thought is to also see if you can use Spark, which we'll talk about in a bit. And then talk a little bit about potentially iterating through multiple versions of the models. You could have start out with a basic model, and then see if you could use hyperparameter tuning, different kinds of approaches, wherein you can figure out which would be the most optimal model for you to use. Okay. So in terms of stochastic gradient descent and clusters, well, in case you are running it on a machine and you don't have the entire data set which can fit on one machine, one thought would be to just use a cluster. And the whole goal is, when you talk about gradient descent, and the key aspect of stochastic gradient descent is the iterative aspect of the algorithm, right? And if you wanted to compute these gradient updates, one thing could be synchronous, wherein each machine computes one piece, and then you put all of them together, right? If you can't fit everything on one machine. Another approach could be each machine applies its gradient updates when they're ready, but that could be potentially noisy. Okay. And then another approach could be let's have every machine compute independently, and they have their own parameter updates. Okay. So there are different ways in which you can do this, and there are different algorithms and papers talking about different approaches, and we'll talk a couple of them on how that's been integrated with Spark. Now, as most of you know, Apache Spark is a distributed platform for large-scale distributed computing, and the key value proposition for Spark is compared to that of traditional Hadoop, because of the in-memory abstraction of how computation is done in memory. It's supposed to be 100x faster compared to that of doing it on a disk, right? Now, as you know that Apache Spark has these independent stacks built on it in case you wanted to work on streams, in case you want to work on machine learning problems. You have different packages you could use. You can even use some of these Spark packages created independently and use on Apache Spark. So that's where a lot of companies are thinking about how do we actually leverage this architecture to see if we can scale deep learning applications. Okay? A couple of approaches people have thought about is, well, the key drivers, right? So one of the things to think about is, well, people have already made significant investment in the enterprise in Apache Spark, and now GPUs themselves, it's not easy to kind of integrate GPUs into the enterprise IT stack. So you have to have dedicated machines with NVIDIA cards on them. It requires specialized hardware. It's not a generic use case which everyone would need. So how do we actually integrate these niche use cases? And now deep learning itself is actually a niche application for many companies. It's not like a traditional bread and butter kind of an application. So how do we build specific architectures? And one of the key questions people are asking is, can we use deep learning applications and leverage the existing Spark architecture we've already built out, rather than just starting to source dedicated hardware for the whole thing, right? So a couple of things which have happened. On Databricks side, I'll talk a little bit about some of the things which are happening on their platform for running Spark applications. There's a library called as BigDL, which is Intel's library for deep learning for different distributed frameworks. There's something called as TensorFlow on Spark, which was open sourced by Yahoo recently. And that's another Spark package which could be used for distributed deep learning for big data clusters. And there are a couple of other traditionally academic / independent approaches. One is called as SparkNet, which actually came out of AmpLab, which was the lab where Spark originated, but a couple of graduate students were working on creating like a framework for training deep neural networks on Spark. There's also deep learning for J, which uses, there's a typo there, it uses data parallelism for training deep neural networks. There's also DeepDist, which is basically it applies, uses Spark and applies gradient updates via parallel stochastic gradient updates. Okay. So let's kind of take a deeper look into it. In terms of Apache Spark, they basically taken this inception algorithm, and what the claim is that if you deploy to these trained models, so you basically take your trained model, and it's the goal is not to just use Spark for training, but in terms of after you have a trained model, how can I use this trained model to basically use it for classification, right? And that's where they're using Spark, wherein you basically have this inception model, which you can go to TensorFlow and you can download it. And once you have this trained model, in order to do a prediction, apparently it requires like 4.8 billion operations, and that's where parallelization could help. Rather than you doing it on one node, you just basically parallelize it, and then you kind of do your predictions on multiple nodes. So you don't use Spark for training, but you just use Spark for doing scaling and parallelizing. Okay, another approach is basically distributed model training, and that's another thing you could do with Spark. What you could basically do is let's say you have the simple MNIST problem, and I have multiple models in training. So it's kind of a crude ensemble model, if you will, wherein I'm using Spark and I'm basically training different models, and then I choose one model which works best. Okay, so you could basically set up your grid of potential experiments you want to do, and then you can basically use Spark to run each experiment independently. Okay, so here you're basically doing a task parallelism. Rather than doing one operation, you're kind of running multiple operations on multiple nodes.
Doesn't TensorFlow has its own cluster mechanism?
In what sense?
Like TensorFlow itself. Does it know other machines? Like clusters?
No,
No?
not inherently. I mean, like there are newer, hopefully as TPUs and other, hardware innovations happen, there may be some TensorFlow specific packages, but right now, you have to basically manage all the aspects. Yeah. Okay, they also have something called TensorFrames, which is basically, you have your data frames, Spark data frames abstraction when you use Spark. So this TensorFrames mechanism kind of gives you the ability to actually manipulate your Spark data frames. And they have the Scala and the Python bindings for it. So it's a Spark package. Basically install that Spark package, which if you have your data in Spark and you're trying to manipulate, so it gives you a bridge to using TensorFlow along with Spark data frames. Okay. So that's another way you could potentially approach scaling problems. One other, Intel, typically has its own architecture. I haven't included any of the Nirvana stuff in here on the deep neural side, but they have what's called as BigDL, which is actually an open source distributed package for Apache Spark. And they're talking about feature parity with Torch and Caffe. And if you basically get this BigDL, you can take your Spark core and you can basically install it as a Spark package. And it primarily uses MKL, which is Intel's math kernel library for multi-threaded applications for each Spark task. And primarily the use case is, if you're training really large scale models, it uses distributed synchronous mini-batch stochastic gradient descent. So you're basically distributing it in a synchronous way. I talked about synchronous, asynchronous, independent approaches. So it basically uses distributed synchronous approach for computing your mini-batch gradient updates. Okay, and I've just kind of taken this statement verbatim. The key value proposition is, rather than you doing training on a network which has GPUs on it, and then using Spark for scaling, why not use the same Spark architecture where you can use both the same architecture for both training and for scaling your model. Okay. So rather than, a lot of companies are now thinking, well, should we have like a GPU-based cluster for doing training, and then we want to do predictions, we want to potentially try and use things like Spark. So here it basically lets you do both of them with the same architecture. A similar approach, is kind of advocated in Yahoo's recently open source project called as TensorFlow on Spark. They already had an approach for Caffe on Spark, but they recently open sourced this project called TensorFlow on Spark. And basically what it does, you have your data in here. So if my data is in Hadoop, so this is basically where I'll prepare my data sets for Hadoop. And then people what typically do is, if you have your data in Hadoop, you move it to a deep learning cluster, you do your training, and once the training is done, you take the model and put it back onto your Spark cluster, and there you apply your deep learning model, right? So if, let's say, I'm doing large-scale image classification, so I basically bring in all my images to my deep learning cluster, build a classification model, and then deploy it. And then when I get like large images which I need to process, I use my Spark cluster to do my tagging or my classification. So rather than using two different architectures, the thought is basically have this TensorFlow on Spark on the same cluster, Spark cluster, wherein you can do both your training and your classification in the same place. So this basically enables both asynchronous and synchronous training, and it supports both model parallelism and data parallelism because you're kind of doing everything in the same place. Okay. So those are a couple of approaches, and I didn't talk a little bit on the other approaches. There are three other approaches which I haven't seen much traction. SparkNet, for example, after the graduate research was done, there wasn't much progress on the project itself. There's a GitHub submission, but nothing has happened since then. The same thing with other ones. I haven't seen a lot of traction, but there could be independent efforts to get these projects off too. But I've been focused mainly on the ones which are in some way associated with TensorFlow, because that's kind of the most popular application at this point in time. Okay. So any questions on kind of combining deep learning approaches with Apache Spark? It's relatively early. I mean, there are hardware innovations. There was a recent update on AMD coming up with a new chip to compete against NVIDIA's efforts. And again, Intel is working on the Nirvana cloud and other stuff. So we don't know where this is going to lead. But right now, companies have to answer the question in terms of investments. Like if they've made investments into Spark, so do they source another hardware? And what amount of performance will that NVIDIA's chips give, or can they live with basically doing distributed clusters and working with algorithms at the scaling and whatever prototyping they're doing at this point in time, right?
Does it seem more common for companies? So since a lot of this is pretty new, like with
right,
scaling this up, does it seem like most companies, since you can build a pretty good model and try to sample of your data, is that maybe more of a common approach today? You're just kind of sampling, building a model, and then deploying it and see how does it perform on the rest of my data, something like that. Does that make it more common?
So unless there is a very specific use case for deep learning, which requires dedicated hardware, and at that point, companies are specifically focused on DGX 10 kind of architectures, and focusing on having like a cluster of CUDA compatible SLI cards and stuff like that. But if some of these companies are trying to explore opportunities of using deep learning, so at that point they really are not inclined towards making an investment towards going and investing in GPUs, but they want to get the scale, because running it on a single machine with just leveraging the cores on your system may not be sufficient enough to really test out those use cases. So this gives a good mechanism where you can still use parallelism. You may not get like 15x or 20x performance, but you can at least get like 4x or 6x performance and work through those use cases. Okay. Okay. Some other aspects which you need to think about when you're doing deep learning networks, especially in an enterprise setting, is primarily figuring out what kind of operations can you do, right? because as you can foresee, when you're building deep neural networks, you have a lot of knobs you can operate on, right? So in the last session, we talked about a lot of these performance parameters you can tune. And you could also use Spark to independently train different models, or you could think about training different models and iterate on them. So one of the things you need to think about is, well, how do we actually version control these models, right? And then how do we train these models and figure out whether the models are actually working fine, right? And once you find that the model is not working fine, how do you actually look at it from a production perspective? When do you say that you need to retrain your models, right? And then also figure out like how my input characteristics are changing, because if you're working with a really large data set and let's say the characteristics of the data itself starts changing, right? How do you actually go about figuring things out? So we have been putting in some effort in that space, and we're putting together an architecture to basically leverage some of these components. And the goal is to containerize some of these applications, so that way you can actually use a front-end application to figure out the various knobs and do auto-tuning of various parameters, so you can independently run multiple tests, both up on using Apache Spark and using Docker-based containers, and then figure out which parameters are the most optimal parameters for your model to be deployed. Because right now, that's a challenge. You have to manually do everything. So we are actually experimenting with an architecture. It's not fully ready yet, but our goal is to basically provide you an architecture which will help you to do model validation and also doing some stress testing and validation and looking at different aspects. And if you wanted to do an asynchronous test on running multiple models and figure out which model works fine, we are kind of thinking about putting together an architecture and doing these things. So if there are any questions related to that, let me know. We can do a demo. It's kind of not fully related to the deep learning stuff we are doing, but it's kind of a use case we are planning to address with this particular architecture. Okay. So that's all I had for you guys. Any questions before we move to the next segment?
I guess, well, you said that is there any specific that you would concentrate for us if we were to as a frame?
I think, yeah. So if your use case is to primarily go for Apache Spark with, yeah. And I'm sorry? And Keras, yeah. So I think TensorFrames is a good place to start, because it basically gives you the bindings. So you can use the Python bindings to start working directly with Spark data frames. For cross-validation kinds of use cases, wherein you are basically setting up your architecture so that you can run multiple experiments, that could be done pretty easily. You don't even have to use Spark. But in case you're planning to use Spark, if your data is already resident in Spark, then that's a good use case to test out too. And the inception example I showed you earlier, that's another good use case, especially if you're trying to do distributed model prediction. If you already have a trained model, like you're using an inception model or any kind of ImageNet model, and you're primarily saying, well, I've trained my model and I need to be basically doing tagging of images or classification for a million images. Right? So at that point, you can potentially deploy it on a Spark cluster and try it out. Right? Other ones, I think many of them are still in a research phase, so you can definitely try them out. But again, it's subject to experimentation. Yeah.
I don't know if you guys, so you guys will cover it or not. Are you gonna, tell us how to put it in production? Let's say I have a model, TensorFlow or something, but our production in C++. Let's say, how do I make it so that they can use their code, C++ code, let's say, to communicate with my application?
Yeah. C++ with TensorFlow. I don't think I've worked with C++ with TensorFlow.
Actually, TensorFlow is written in C++.
But is there a model which you can?
I think short answer is there's a lot of stuff that's really specific to your deployment. So there are some guides out there, how to deploy TensorFlow. But if you look at And then beyond that, it's going to depend on your environment. We can talk during the break if you have specific questions. But how to do large scale machine learning sort of operations would be a whole separate workshop on all these different things. So we can hit some specific points if you have questions, but I don't think we can really cover general recommendations besides what we already mentioned. I mean, always know what the model is, know how you're going to tell whether it's actually working in production or not. Like that.
Yeah, there are also these export mechanism companies use. There's a format called as PMML, and you would actually export once you've built out a model to like a PMML format, like the train model, and then use the train model for deployment outside, right? And the deployment mechanism completely separate from the training mechanism. So ultimately, your whole goal about training is to kind of get to a model, right? And then you could basically take that model, put it onto your hard disk. And when it comes to your deployment piece, you just basically bring that model back in, and then you use it for your prediction. Right? So there are some approaches, using ways in which you could basically train it in one environment and kind of deploy it in a different environment. So those are some things people typically do, but we can talk about it offline. Interesting.
Yeah, I believe the most of the effort that are based on training is building a model. And but to use a model to decode the model, actually, is straightforward. Most of the CPU resources, because what used to develop a model, because for example, you don't know how many layers you need, how many pooling you need. What is the first layer you want to use a 5x5 and with 30? There are too many parameters. You need to decide, right? So that's why Victor said you can use existing whatever architecture already exists. You can borrow from there, and then you can do the last part to modify the multi-layer perception. Let's do additional decoding, the training. So to decode the model, I don't think that is that difficult. So whatever available.
You're talking about deploying or decoding?
I think
deploy is very
Right.
straightforward.
Yeah.
I think it's the question isn't so much computational capacity as just the mechanics
And the aspects of.
getting all the stuff set up and installed and on the right servers and moving files back and forth. So it's really general kind of software operations that isn't really very specific to model.
And it's also model specific. For example, if you built a pipeline, which involves basically, let's say we talked about autoencoders. So if your pipeline is such that you're basically getting the data, passing it through an encoder, and then you have this hidden representation. Take this hidden representation, pass it to another algorithm, which does your classification for you, right? So you set up a pipeline such that you basically need this hidden representation. Now, what is this model which is going to give you this hidden representation? You have to use an alternate training mechanism. And then you build out an autoencoder architecture, which you generate a bunch of weights and biases so that when your new data comes in, you need to pass it through this network so that you get this hidden representation. So you're setting up a pipeline which does that, right? If you're talking about like general images and you're just tagging general images, then you're probably requiring this large corpus of images, and then you're basically first resizing them to the same size. You need to do some pre-processing, get it to some kind of a form, then you do your training, and basically going through all the steps we've been discussing for the last day and a half. But approaches in which you can optimize your algorithm. Once you have a good algorithm, then you'll think about deploying that particular algorithm. So you basically design those pipelines.
For Apache, I have a question for the Apache Spark. I don't have experience on that. Is that something similar to TensorFlow, Chaos? They have some API you can call?
Yeah, so
things?
It's not, so in terms of what to you is, so let's say your data is in Hadoop, right? And your goal is to figure out, well, I can't bring everything onto it's on the same machine. It's distributed on multiple machines. And let's take a very simple example. You want to do a map reduce kind of an operation.
Yeah.
Take a very simple word count.
If I have a 10 terabyte of data,
right?
I cannot run on one system.
Exactly.
So I have to run
exactly. So you're basically setting up. Yeah. You're basically distributing your data onto multiple nodes.
Yeah.
And then what they do is they basically have this architecture called as RDD, resilient distributed data sets. And it provides you things like fault tolerance. It provides you the ability to basically.
But that's Hadoop, right? That's
Well, the whole thing is the whole architecture is built on in-memory. It's an in-memory abstraction. Hadoop is not in-memory.
Can I try to answer? I think, and tell me if this is actually right, if you know more about Spark than I do. I think of Spark as Hadoop 2.0, right? It's Hadoop, except it keeps stuff in memory,
yeah. So
and so it's much faster. So it's still a general purpose parallel computing infrastructure.
yeah, similar to that. Although that
The data is still in HDFS.
Yeah.
It provides you in-memory abstraction. Plus, it also provides you all these other things. Wherein instead of you just, in the traditional Hadoop architecture, what you would do is if you wanted to do a map operation, you do a certain operation, you put it to the disk.
Yeah.
The next map operation, take it from the disk, you do another operation to put it back to the disk.
Yeah, so
Writing I/O is going to be
yeah,
expensive.
so-
Spark solves that problem by doing everything in terms of, and basically sets up a graph. It's basically a DAG, and it does like stage by stage, and keeps everything in memory.
Yeah, but the question is, when we talk about deep learning, I mean, you cannot really do the map reduce use deep learning.
Well, you're not talking about doing MapReduce. You're primarily talking about if you're doing distributed
Yeah, this,
learning. So the SGD computation, when you're doing SGD, so that's where these packages come in handy to do distributed gradient updates.
but how,
So, right, normally when you're doing learning, you take a batch of samples, right? I take 128 samples.
Yeah.
I compute.
I
I do a forward pass, and do a backward pass. I compute a gradient update. So, okay, update the weights like this.
Yeah.
Then I go to the next batch.
Yeah, but I cannot do distribute, right?
So you can,
how?
right? So there's two ways. One is basically, if I have 10 machines, just take 10 batches, put a batch in each machine, compute 10 different gradient updates,
But
just
how
add
do
them all up.
you,
It's not quite perfect, but if you're talking about doing a pass through, 100,000 training examples, if you do 10 parallel batches, if your learning rate is small enough, they're still all going to be roughly the same, hopefully the correct direction. And so you can just add up all the gradients, make an update, and then do 10 more batches. So that's synchronous. And even crazier, which also kind of works, is just run your 10 machines in parallel, grabbing batches as soon as they can, and just add your gradient updates as they come in. On top
Okay,
of each other.
so
right?
you
They
talk
overwrite
about-
each other, but overall you're still hoping that you're kind of roughly going in the right
so you
direction.
want to do the parallel job, and each batch give you one gradient. So right now you are doing the update based on your learning rate times the summation of all the gradients.
Right.
Yeah.
Yeah.
And so
Okay,
again,
that
it's
makes
not theoretically it's not quite justified because now you're taking steps from the wrong place. But if your learning rate is reasonably small and your function is for the most part reasonably smooth, you still end up going kind of in the right direction. And the benefit of parallelization hopefully helps out and makes it worth the slight loss in accuracy from doing, sort of not quite the right steps.
There are different approaches. Kind of about distributed, synchronous versus distributed asynchronous. So some of these packages, they have like different approaches. So you can actually treat them and say some of them are better than the others, kind of thing. Okay. Cool. Let's take a break now. It's 3:15. We'll rather 2:15. So we'll take a quick break, like 15 minutes, and then come back and go for the rest of the sessions. Cool. Thank you.
Turn off the